all the substrates that you need to know, and if you already knew it in 231, now it's just a mind refresher. But ostensibly what you're doing is, and you have to recognize some of these chemical intermediaries. Even if you're not a chemistry fan, these are like friends. Think of them as friendly intermediates. And you got to remember some of these. Some of them are more important than others. So when you go through the first steps in glycolysis, you remember that you start off with glucose and then you phosphorylate it. So here you start with glucose, you phosphorylate it on the end side. And bear with me if I'm telling you something. I'm not going to try to insult your intelligence, that I know some of you already went through this with me, but I just want to go through this again for my own personal benefit and yours. How about that? All right, so the first thing you're going to do is you're going to phosphorylate that, and then that's going to be called glucose 6-phosphate, because when you put a functional group on here, that's then going to get that naming feature. So then what you're going to do is you're going to add a second molecule in there. You're going to rearrange this. So this is a little molecular rearrangement where you convert it into fructose 6-phosphate, 6 still being the place that has the phosphate on there. You add another phosphate on there, and now you have fructose 1,6-bisphosphate. So it's got 2 of them on there, one on the number 1 carbon, one on the number 6 carbon. So then you have an enzyme that has the capability of asymmetrically splitting this molecule. So it's going to create 2 molecules. One of them is glyceraldehyde 3-phosphate. This is a very important one. Put a star on this one. The other one is temporarily going to be created as dihydroxyacetone phosphate that after a very short period of time will also get converted into a second molecule of glyceraldehyde 3-phosphate. So now I'm showing you this process. These are both exactly the same of this happening to one glucose molecule that now has 2 molecules of glyceraldehyde 3-phosphate. You have an energy carrier, NAD, is going to interact with this molecule, steal a hydrogen, and become NADH. And when it does that, it's going to add another phosphate on there. So now you're going to have a biphosphorylated molecule. It's 1,3-biphosphoglyceric acid. 1 phosphate on the 3 carbon, 1 on the number 1 carbon. So then you go through this series of steps where you're going to take those phosphate groups off. So here you take off the 1 from the number 1 carbon. This gives you 3-phosphoglyceric acid, and you make a molecule of ATP in there. You go through another rearrangement now where you take this phosphate, so after you've got the first phosphate off, you have a rearrangement molecule. It's called an isomerase, where now you're going to move that phosphate onto the number 2 carbon. So that's called 2-phosphoglyceric acid. So now it doesn't have that one anymore. Now, and this one doesn't have this one. So now you have this situation where you have an enzyme that can easily get that phosphate off there. It'll create it into phosphoenolpyruvic acid, take off the last phosphate, so you get the second molecule of ATP produced, leaving you then with pyruvic acid. So here you get 2 ATPs produced here, 2 ATPs produced here. You kicked in 2 up there, you get 4 back here, so now you're ahead of the game with 2 ATPs. But more importantly, you've created this molecule, pyruvic acid. So then what you're going to do is, and this is all in the cytoplasm, then you're going to go through this lipid bilayer in the organelle called the mitochondria. So here you've got 2 membranes. Remember when you ever see, like in 231 or in your book, if you look at this, you get a mitochondria and they symbolize it with some kind of thing like this. This is to recognize that there's an outer mitochondrial membrane, which is a phospholipid bilayer, and then there's an inner mitochondrial membrane, which is what this is. So here's the outer mitochondrial membrane, here's the inner mitochondrial membrane, with these cytochrome enzyme chains. This is where the electron transport chain is going to be. So you take the pyruvic acids in, you get those NADHs that you had from your energy carrier that you had reduced, and now you're going to get that hydrogen on the other side in this intramembranous space. So you got to find one of these molecules that's going to take that for NADH, take that molecule off and oxidize it to get it back in the NAD form. If you get the NAD back out into the cytoplasm, then you can do glycolysis over and over and over again. You only have so much NAD, so that's why you have to do this. All right, so once you get this down, you get pyruvic acid into the mitochondria, it's going to interact with a molecule called coenzyme A. Coenzyme A is going to combine with it, cut off a carbon. So remember, pyruvic acid was a 3-carbon molecule. Now it's a 2-carbon molecule. Here's your carbon dioxide getting given off. And then you get a molecule of NAD reduced to NADH. Now this is showing you that it's coming up here, and this first enzyme here is called FMN. And FMN of the electron transport chain on that inner mitochondrial membrane is the enzyme that's going to take NADH, split off that hydrogen, and transport that hydrogen ion into that intramembranous space. That's what FMN does. And down here on the bottom, you have a picture of that. So here they're all labeled. FMN is the first one. This little one inside that membrane is coenzyme Q. That's what's going to oxidize FADH2. And then you have ATP synthase, which is going to be the critical one that these hydrogen ions are going to want to come back through there through the process of chemiosmosis. Remember that? And now they're going to activate this enzyme channel to take ADP and any phosphate that you've absorbed. Remember from the phosphatases that we had in our digestive process, when you break off phosphate groups, you absorb those. That goes in your blood. That's going to go in these cells, and that's where you get the phosphate from. And then you're going to make ATP out of that. This is where the bulk of your ATP is made. The bulk of the reduction steps that's going to generate all these steps, you have all these little intermediary steps here that are going to take some molecule, take a hydrogen off it, and then give you your NAD back. That is going to then generate hydrogens that you can transport across here. So you always have a buildup in the mitochondria in that intramembranous space of hydrogen ions. So that assures you that you're going to get these molecules wanting to come through there by the process of osmosis, going from a higher concentration in the intramembranous space to a lower concentration out here. Once they come through here, you have oxygen that you've been breathing, and it's going to combine with that oxygen to give you metabolic water. What do you think of that? Now here's the beautiful thing. Let's make a couple of connections. Remember when we talked about respiration? And you guys looked at that equation inside the red blood cell, and we talked about the partial pressures of why things are moving the way they do, because they're going from higher concentrations to a lower concentration. And remember we talked about the fact that when you have a cell actively working, it's producing carbon dioxide, so you get the partial pressure in tissues of carbon dioxide was the 45, but in blood it was only 40. That carbon dioxide is coming from this step, and from this step. And as you're metabolizing sugars and other chemical compounds, you generate, that's where the carbon dioxide comes from, that makes that partial pressure higher, that's going to go into your blood. And the reason why cellular respiration is called cellular respiration is because you have that partial pressure of 100 in blood, 40 outside of these cells, so that oxygen's going to come in there, but that's not the end of it going through that artery to get next to some tissue. It goes into that cell, and that cell now can combine that with these hydrogen ions that are coming across that membrane so it can keep doing cellular respiration. That's the connection here. That's the connection between this and respiration. Anything, any of those respiratory diseases, the COPD diseases that inhibits oxygen transfer, is going to affect this, and it's going to slow down your ability to make energy. You're going to manifest this by being a little tireder, by getting more fatigued when you do regular things. This isn't some esoteric set of chemicals that are some weird little thing that somebody came up with and said, boy, let's make this an insanely difficult thing for students to kind of learn, and there's no connection. This is real important stuff. And it's not disconnected, it's connected to everything. Remember this. We just talked about the dynamic of moving oxygen in from the air into blood and then into tissues, and then we left it off there. This process that's happening here is not some weird little process that happens in one cell. This happens in every cell in your body. The sleepy little chondrocyte, the highly active osteoblast, nerve cells that are making neurotransmitters. Everybody does this. And everything has to do this. And if they can't do this, or they can't do it as well, you will show up with the symptoms of the inability of your cells to do those particular tasks, depending on which cell is involved. You get the decreased circulation of oxygen up to your brain, and when they talk about your brain cells dying, if you get them deprived of oxygen for 5 minutes, yeah, that's true. But you don't have to deprive them of all the oxygen. You don't have to kill them. You can reduce that blood flow up to your brain by half, and you will be very, very tired, very mentally confused. You'll have all kinds of CNS problems, still having blood flow there, but inadequate blood flow. So this is like hugely important stuff. So in 231, you had to know these steps that you go along the rim of this. These all have different carbon numbers. So oxaloacetic acid, which is going to be your initial acceptor molecule. So coenzyme A is an enzyme that doesn't really want that 2-carbon fragment that it now has, that acetyl group. So it's going to add that 2-carbon to this 4-carbon to make you citric acid, which is a 6-carbon molecule. Isocitric acid is a 6-carbon molecule. Alpha-ketoglutarate acid is a 5-carbon molecule. And then all the rest of these are 4-carbon molecules. That's an important thing to remember, yeah.
So coenzyme A will combine with
Acetyl coenzyme A is going to combine with oxaloacetic acid, add that 2-carbon fragment, and then run away like a good enzyme would to go back and do that again with pyruvic acid and steal another 2-carbon fragment.
So that triggers the whole citric acid cycle.
Yeah. Once you start this, then you have enzymes. I didn't put this in here just to not clutter this. If you take biochemistry, if you learn this at any point, hopefully you learned this, and I hope most of you spent a fair amount of time where this is like, oh yeah, I got to dust this off, but I kind of remember most of this. When you take biochemistry, the thing that really makes things go is that you make all these enzymes to grind this wheel.